announcement. So let's click over to the course schedule real quick. If you look under April 22, you will see the following. This class will not meet on April 22. No math class will meet on April 22 at this university. That's because April 22 is the day of the math retreat, which, if you like, is the math department's portion of the university's celebration of student research. So there will be a bunch of math talks being given instead, some of them in this very room. There should be a link right here to the math retreat schedule. There is one posted in Canvas. In the meantime, there's the math retreat schedule. Take a look at that. It's got some titles and abstracts for some talks. A bunch of them are happening during this very class time, so I know for a fact you're available for some of these talks. So you can't tell me that you can't make any of the talks because you're lying to me if you are. Probably. That's a little glitchy to me. Anyway, so if you attend some talks on the math retreat day, then make some time and just come by my office and have a conversation about the talk. I don't expect like a perfect understanding of what happened during the talk. Just come by and tell me about it and we'll have a bit of a conversation. You'll get some extra credit points. The other source of extra credit associated with the math retreat is, and these are both posted in Canvas, so check out Canvas for details. There is a math competition at the end of the day during the math retreat. Some of the problems are going to require some amount of calculus knowledge. Some of them, like, you won't know what the symbols mean, which is fine. But I know for a fact that a bunch of the problems are. So if you want to put some teams together, shoot me an email. We'll get you some points for that. And exactly how you get points is also detailed in Canvas on that front too. Cool. Any questions about just that? All right. Nice. Anyone think they'll try to take me up on either of those points? All right. The only one you have to tell me about in advance is if you plan on coming to the math retreat, because I'll need to get you registered either as an individual or in a team. So shoot me an email with those details. You can't just ask to be an individual and then I'll put you into a team. If your team is only 1 or 2 people, then there'll be some other people who have signed up without teams that I'll just lump you in with. Cool. And the math retreat competition is probably the lowest time investment way of getting some points, because you just have to come and be present and engage for like an hour. Neato. That being said, well, I guess any questions on that point? Cool. Then, let's start doing some content. So the other thing I'll have to say is I'm going to need to apologize for a certain amount of absent-mindedness on my part today. My dog had me up from roughly 1:30 to 3 this morning, and then I have an alarm that goes off at 5:30. So I'm a little shy on the sleep cycle side. But let's begin. So we're talking about inverse trigonometry, and let's just remember the job of the inverse trig functions, and they're written on the bottom. So if I ask you to compute inverse sine of a number, the general strokes of what this should be is built into the notation. It should be an angle whose sine is y. But there are lots of angles whose sine is y. This only becomes a function if you specify the range that it has to live between. What does inverse sine of y have to be in between?
Negative pi over 2 and pi over 2.
Negative pi over 2 to pi over 2. And if you would like, for From the unit circle perspective, that makes sense. All of the y values are achieved in those two quadrants. Similarly for cosine, inverse cosine of x should be an angle whose cosine is x. But there are lots of angles whose cosine is x. What angle should it live in between?
0 and pi.
0 to pi. Or 0 to 180 degrees if you like degrees. There's 0 to pi. Yeah, that looks like all the x values on the unit circle are achieved in that range. There are lots of applications of these things. The most obvious one comes from determining an angle given some triangle instructions. So here's one. Suppose you want to build this triangle. You know those two side lengths, you know what they're supposed to be. It's going to be a right triangle. But like, I don't know, maybe you're like building these out of wooden planks and you need to know at what angle you should cut that joint. How could you figure out that angle? Well, I asked you to do this one like at the end of class last time, right? Anyone actually do it? Cool, what'd you get?
If we're going at that angle of alpha, that's alpha, right?
Yeah.
Okay, yeah. If we're going based off of alpha, then you could do sine of alpha equals 7 rad 65 over 65. Because to find c, you have to do 4 squared plus 7 squared equals c squared.
Cool, so what would alpha be? Inverse sine of that number.
Oh yeah, inverse sine of 7 rad 65 over 65.
Because right, that's the whole job of inverse trig functions. Inverse trig functions give you the simplest angle that achieves that value for a trig function. How'd you get this 7 root 65 over 65? Let's just go through the walk.
So you want to figure out all the signs. So at angle alpha, the opposite is 7, and the adjacent is 4.
Cool. So I guess that means like you need
C is
a
a
hypotenuse.
Yeah.
So what'd you get for the hypotenuse?
Rad 65.
Oh, nice. Cool. With like those things written down, people feel like they understand how to approach this problem even if they didn't when they were supposed to. Anyone want to see it walked? Cool, let's do it. So let's start by finding that side length C. So what equation do you use to find the hypotenuse of a triangle? Pythagorean theorem. So you could find that side length C. You'd use C squared equals 4 squared plus 7 squared. And from there, I guess I'll take your word for it. That's 4 squared plus 7 squared is 65, and then you take the square root. So you know what C is now. You now know that the sine of alpha is opposite 7 over C. Which, okay, yeah, so you'll have a square root in the denominator. So you multiply and divide by what that square root is. That gives you this number. In line with the work you did?
Yeah.
Awesome. Oh, and then like you know what sine of alpha is. So alpha is the inverse sine. There was one sneaky way you could have avoided some of that walk. And we'll verify that it agrees in a moment. Without finding that hypotenuse, what is the tangent of alpha equal to?
7 over 4.
7 over 4, opposite over adjacent. And we haven't talked explicitly about inverse tangent. Oh, cool. So you could just use that formula instead. And then you don't have to find the hypotenuse. And those should give the exact same values. You know, that feel pretty good? Yeah. All right. So let's list the things that I want to do next. So we have these inverse trig functions, and they're inverse functions. So they're trying to undo sine, or trying to undo cosine. But just like square root doesn't quite undo squaring honestly, right? Like there's this plus or minus sign that shows up. The same thing can happen here with trig function of inverse trig function. So let's try to walk out some of the subtlety by just going through it. Let's try to compute something like cosine of the inverse cosine of 1/2. And let's compute it from the inside out, right? Let's not make any assumptions about how these things should undo each other. Let's just compute from the inside out. Take out your unit circle and use that to tell me what is the inverse cosine of 1/2. So let's remember what this is asking. This is asking, what is the angle in between 0 and pi whose cosine is 1/2? So what angle do you see on your unit circle where cosine is 1/2? I hear a pi over 3. People agree? Nice. So that means inverse cosine of 1/2 is pi over 3. And now go back to your unit circle. What's the cosine of pi over 3?
Half.
1/2. Oh, notice like you looked at the exact same place both times you did that computation, right?
Yeah.
That's interesting. Let's play that game like 2 more times. Let's compute the sine of the inverse sine of -1 using the same steps. So what is the inverse sine of -1? Negative pi over 2. Anyone want to say 3 pi over 2 to that?
Or,
No, your answer is the right one.
oh,
3 pi over 2 is the wrong answer.
Oh.
Because it needs to be between negative pi over 2 and pi over 2. 3 pi over 2 would be too extreme. So, negative pi over 2. And what is the sine of negative pi over 2? Oh, neat. And you had to like look at the same place for both of those steps. All right. So it sure seems like they just always undo each other. The next problem, something interesting will happen. Let's compute the cosine of, the inverse cosine of 12. So let's start with this. What angle on the unit circle will give you a cosine of 12? No? What's the biggest value cosine ever takes? What's the biggest x value you see on the unit circle? 1. So is cosine ever equal to 12? So is there an angle between 0 and pi where cosine is 12? So what can you tell me about the inverse cosine of 12? Yeah, it isn't. It doesn't make sense. There is no angle whose cosine is 12. And so, what's the cosine of something that does not exist?
undefined.
Undefined. It certainly isn't 12. Or I suppose I could have equally well put undefined in that blank as well, save myself some space. All right. People think they have a pretty good idea for when trig functions are undone by the relevant inverse trig function? Yeah, I think this about tells us. So, the conclusion here is whenever you see any input for inverse cosine and you want the cosine of the inverse cosine of that input, they just undo each other. Cosine of the inverse cosine of x is always x. I'm going to make this a y just because it's sine, it should be a y value. It doesn't need to be a y. If you don't want to make that change, don't in your notes, it doesn't matter. Sine of the inverse sine of, no, I'm going to leave it x. Sorry if I'm like screwing everything up on your notes. Provided that that x value is in between -1 and 1. Because otherwise the like inside function doesn't exist. Sine inverse of 12 isn't a thing. Nice. All right. So, if you like, that's the easy direction. Right. That would be like thinking about the square root of x and then you square it. And yeah, that always gives you x. provided x is bigger than or equal to 0, because otherwise the square root doesn't make sense. Something weird will happen, right, when you take the square root of x squared. Right, that's where this plus or minus x shows up. Let's see what the corresponding thing is here for trig for sine and cosine. And maybe here's even a place to begin. Here are some computer-generated graphs. One of these is, one of these will be sine inverse of sine of x. One of these is cosine inverse of cosine of x. And let's try to decide which. And let's take like process of elimination approach. There are two options and like two questions. So if I can like eliminate one of them from consideration, then I'll be done. So I'm saying don't use any fancy ideas. What's like something you could do to figure out which one of these is which? What is an input that seems to distinguish A and B from each other? Cool, I think I just saw a 0. Let's see if 0, before we do any computations, let's see. So this graph, when x is 0, seems to go through y equals 0. This graph, when x is 0, seems to go through y equals 0. So will that help us distinguish these two? No, they'll both give us the same result. It would be useful if I had like more options. If I had like a ton of options, you could say, well, any of them that don't go through 0, 0, I shouldn't consider.
We could look at pi 0.
Pi seems to tell us something.
Oh yeah.
X equals pi, this one goes through 0. This one, x equals pi, seems to go through pi. So let's make some computations then. Oh, and I guess that's even indicated in these lines above. So let's try to do it. So same thing, we'll compute from the inside out. What's the cosine of pi? -1. Now I need to know what the cosine inverse of -1 is. To figure that out, let's just reread the instructions. I need the angle that is in between 0 and pi, which has cosine equal to -1. So check out your unit circle. What is the angle between 0 and pi with cosine equal to -1? Pi. Oh, cool. So what's the inverse cosine of -1? Cool. Let's play the same game for sine. Even though I think we know what the answer should be, let's see if it actually works out. So follow the same instructions. What's the sine of pi? 0. All right. Now I need to know what is the angle in between -pi/2 and pi/2. It's a good thing I wrote it down, because otherwise my brain would have absolutely frozen up for longer. Which has a sine of 0. So look at your unit circle. What is the angle in between -pi/2 and pi/2, whose sine is 0? Ooh. So, A and B. So, A is the graph of A's inverse sine of sine or inverse cosine of cosine? Well, let's see. It went through pi 0. So input of pi went to output of 0. By the computation which we just did, which does that correspond to? Sine. And the other one?
Should be cosine.
All right, cool. So that little exercise tells us which of these graphs is which. Maybe just to do a quick verification, convince you that these graphs are actually correct. Oh, sorry, maybe you still want the notes pulled up. There. Desmos. All right, arc sine is just another way of saying inverse sine. That look about like it lines up with this? And this is also like a really interesting shaped graph, right? It has this nice like sawtooth pattern. I guess one thing we see is in between negative pi over 2 and pi over 2, that just looks like a straight line of slope 1. There's the line y equals x as a piece of this graph, which is kind of what you expect. When you apply an inverse function to the original function, you want to get y equals x back. And you do as long as you're at least in the right range. Arc cosine of x of x. Yeah, so it added some extra parentheses, that's okay. We got a similar sawtooth pattern, yeah.
So the graph cosine, does it never like cross the x-axis?
No, it just touches.
Oh, yeah.
And maybe we'll even think about y really quick. So this is start with an x value, apply cosine to it, now take inverse cosine. So this is always going to be an output value of inverse cosine. So this number will always be in the range of inverse cosine. What's the range of inverse cosine?
0 to pi.
0 to pi, always positive.
Okay.
So that's why this output value is never negative. I guess we could have distinguished them that way. This thing achieves some negative y values, but inverse cosine can never achieve a negative y value. So this can't be something that ends with inverse cosine. Neato, that feel pretty good? So one thing you'll notice is, like, that graph looks really periodic and nice, but also like complicated in a way. If I were to ask you, what is the inverse sine of the sine of 273 pi over 7, it should be figure outable. It should be possible to figure out what that is. But it's going to be somehow complicated. Right? This looks like, if you were just trying to describe this as like a piecewise function, it would be like infinitely many pieces, like a bunch of straight line segments. So, like, walking with that would be difficult. But we can still figure out how to walk with things like that. And that's the remaining goal in this bit of the notes, and in fact what the homework is posted for this section. So, let's do that. So to do that, I know that I literally just said what the range of inverse sine and inverse cosine is, but let's remember. What's the range of inverse sine?
Negative pi over 2 to pi over 2.
Negative pi over 2 to pi over 2. Same as these numbers.
Wait, what does, just quickly explain what arc does again? Sorry, like when you said arc sine, what is it?
Yeah. You should interpret all of these like arc trig functions as the inverse trig functions. And maybe I'll give you like a very brief etymology about why. So here's what these things are telling you. So the inverse trig functions are the things that say, well, I'm going to specify what y value I want. And then return the angle. So return this angle. But if you walk in radians, that's the same as returning that arc length. Because, right, radian measure on the unit circle is the arc length. So that's why it's called arc sine. It's saying if I fix the y value, what's the shortest arc to get there? And arc cosine, it says, well, fix the cosine value. What's the shortest arc that gets there? Good question. I like that. Similarly, range of arc cosine is, I'm going to have some color coding because I'm going to draw these in the next lines, 0 to pi. And because these pictures will be relevant in the coming computation, I'm going to draw some pictures. What quadrants does this interval worth of angles trace out? 1 and 4. That's negative pi over 2 starts down here, and then it walks its way up here. And it doesn't matter what order you list them in. I'm going to say Q4 and Q1 because the interval goes from the smallest angle to the biggest, so now it's in order. That's not a point that matters. How about 0 to pi? What range does it trace out? Quadrants 1 and 2. That'll be important for what comes. So remember that. If you want to report an inverse trig function, you need an angle that sits in those quadrants. All right, so let's walk with that. So here is the remaining goal. Let's try to compute something like the inverse sine of the sine of 17 times pi over 30. And I think I'm going to do this 2 ways. I'm going to do this by actually following the logical instructions. And then I'm also going to go over to the Desmos graph and try to read it off from there. So let's do it. So step first, let's decide what quadrant this angle lives in. And how do we do that? Well, 17 pi over 3, it's a big angle. It's bigger than 2 pi. So what I'll try to do is I'll try to write it as a multiple of pi plus a remainder top. And then the multiple of pi will tell me what quadrant it's in, basically. So let's try to do that. 17 pi over 3. Let's do some long division here. What do you get when you divide 3 into 17? 5? With a remainder of 2. 5. 3 times 5 is 15, so you subtract 15, a remainder of 2. So that means I could write 17 pi over 3 as 5 pi's from that 5, plus an extra 2/3 of a pi. Yeah, an extra 2/3 of a pi. All right. So let's try to draw a picture of that and try to realize this as a simpler angle. So the 5 pi, that would correspond to like 5 half revolutions. So 1, 2, 3, 4, 5. So the 5 pi will get you to here. Nope. To here. And then I need to go an extra 2/3 of a pi. So there is a ray pointing in the direction of 5 pi plus 2/3 of a pi. All right, which quadrant does that live in? Fourth quadrant? 2/3 is bigger than 1/2. That's why 2/3 is as big as 2 pi over 3 is as big an angle as actually. Nice. And in fact, I could realize that same point on the unit circle via a simpler angle. Looks like I could get there by rotating down just a little bit. How far down? How much farther would I need to go to get back to the, oh, I'm pointing the right way for me, the wrong way for you. So right now I'm down here at 5 pi plus an extra 2 pi over 3. How far would I need to rotate to get back to the positive x-axis? An extra pi over 3? So that means I could get down there by rotating down by pi over 3. So, I can realize this is a simpler angle. Negative pi over 3. All right, so that's what I mean by throw out any excess 2 pi's. That's exactly what we did. We wrote this down as the simplest angle possible. And now, let's ask ourselves, that angle, Does it sit in a quadrant that is acceptable to inverse sine? It sits in quadrant 1 or quadrant 4, right? Yes. If it didn't, then we could preserve the sine while getting it into an acceptable quadrant by reflecting over the y-axis. We don't need to this time. So in this case, the simpler angle we get is still negative pi over 3. All right, and here's the final check. Negative pi over 3. Is that literally in between those two angles? Negative pi over 2 and pi over 2? Oh, cool, that's an acceptable output. So the inverse sine of the sine of 17 pi over 3 is negative pi over 3. Because that's the simplest angle that gets us to the same sine as negative 17 pi over 3 did. And in order to check that, I'm going to go over to this little Desmos demo. All right. I want sine, and I want x equals 17 times pi over 3. Yeah, that's good enough. That's a big number, so it's off screen a little bit. Looks like that y value is negative 1.047. Is that the same as negative pi over 3, give or take? Yeah, pi is a little bit bigger than 1. So like, that seems right. And you also have a calculator, so you can compute it. That feel pretty good? Nice. So here's the game. If I ask you to compute inverse trig function composed with trig function of some silly big angle, step 1, turn that silly big angle into a less silly big angle by throwing out any excess 2 pi's. After that, ask yourself what quadrant it's in. If it's in an acceptable quadrant, great. If it's not, then do the right reflection to get it into an acceptable quadrant. And maybe we'll even add this. Reflecting over the y-axis, what would that do? What does that do to an angle? I would replace negative pi over 3 by, let's see, I want to reflect over the y-axis. So that's like, instead of rotating up in the positive, well, I guess it's down. Instead rotate over by pi, and then rotate the same amount but in the opposite direction. So if that were going up by theta, this would go up by negative theta. So this would amount to replacing negative pi over 3 by pi minus pi over 3. But I didn't need to do that on this particular example. Next example I will. All right, let's do one more. And then we'll see what people want to do. So let's compute, oops. I don't think I need Desmos up at all for this. So here's one that will go very similar, slightly different because it's a different function. Let's try to compute the inverse cosine of the cosine of 17 pi over 3. So, step 1, throw out any excess 2 pi's. We already do that? Yeah, what do you get when you throw out all the excess 2 pi's? Five pi plus 2/3 pi, and we even drew a picture, and the picture got us like there. So what's the simpler angle that gets us to that exact same point? Negative pi over 3. So far exactly the same walk as we did previously. If you like, what we just found is what's often called a reference angle for this angle. We found a simpler angle that gets us to the same point on the unit circle. The word coterminal is often also used because that's a new angle that has the same endpoint, which like a fancy Latin speaker would call that a terminus instead. Hence coterminal. Does this angle sit in the correct quadrant to be in the range of inverse cosine? What quadrants give the range of inverse cosine? 1 and 2. Does that quadrant sit in quadrant 1 or quadrant 2? No. That's bad. That means that the final answer cannot possibly be negative pi over 3. That would not be a valid output for inverse cosine. How can you change that to a new angle? Let's draw a picture. I need to change that to a new angle that has the same cosine value, so the same x value. So I'll draw a vertical line at that x value, and is in either quadrant 1 or quadrant 4. What could you do to that angle to get it into quadrant 1 or quadrant 4? Reflect over the x-axis. And let's think about what that does to angles. I guess one option here is like, we literally wrote this down at like that lookup table about symmetries of trig functions. So either look it up there or think about it. If you reflect over the x-axis, how does that change an angle? So let's see, like, there's rotating up, and there's the result of reflecting it over the x-axis. How do those two angles compare?
Both have the same x value.
Both have the same x value.
Y values are flipped.
Y values are flipped.
Um,
But how do the angles themselves compare? They're negatives of each other. When you reflect over the x-axis, you can do so by just sticking a negative sign in front of that angle. So in this case, that means I want to replace negative pi over 3 by negative pi over 3, which simplifies, of course. What's negative pi over 3? Just pi over 3. And pi over 3 happens to be like an angle that you see on the unit circle. Look at an angle of negative pi over 3 on your unit circle, and also look at an angle of pi over 3. Do those both have the same cosine? Awesome. All right, so we've now gotten it into the right quadrant. So it's at least in the right quadrant to be an output value for inverse cosine. There's one last check to make. Is that angle actually in the range of inverse cosine? Yeah, it needs to be between 0 and pi. It's certainly positive, and less than pi. So, let's make a conclusion. So what is the inverse cosine of the cosine of 17 pi over 3? Positive pi over 3. And I think it's worth taking a moment and just checking that. So, I'll play the exact same game. Look at a graph. So now I have cosine of the cosine of pi over 3. I've picked out an x value of 17 pi over 3. The y value of the point of intersection is like the output value, right? So does that look like it's pretty close to pi over 3? Yeah. Either you've taken out a calculator and computed it, or else pi is about 3 but a little bit bigger than, so the whole thing should be a little bit bigger than 1. Neato. So I think with 10 minutes left on the clock, I think instead of starting up the next topic, because the next topic it's similar to this, but it'll feel different. I think it makes sense to either have you all go through one computation, and then we come together with like 4 minutes left on the clock and talk through it, or if people would rather I talk through a computation. Should I talk through one more? Cool. There are 4 options there. I guess now one from the top, 1, 2, 3, 4. First one. Second one. Third one. Fourth one. I guess like it was a silly vote, right? Like you can't tell the difference between like the complexity of them. I think the first one had the most votes. Let's try that. So let's see, I want to compute sine inverse of the sine of 25 pi plus pi over 5. So notice I've already done like the long division step from the previous one. All right, so 25 pi plus pi over 5. Does that have any excess 2 pi's we could just get rid of? I mean, it does, right? There's something like a 24 pi in there. So here would be one way to picture it. The 25 pi, that amounts to 12 full revolutions, plus a half a revolution, plus an extra pi over 5. So 25 is odd, so 25 pi will get us there. Plus an extra pi over 5. Pi over 5 is a pretty small angle. All right, so now what do I want to do? I want to like get rid of a bunch of excess 2 pi's and rewrite that as a simpler angle. What simpler angle would you want to write that down as? There are 2 sensible answers, I think, to discuss. Negative 4 pi over 5 is 1. How many people would rather write it down as 6 pi over 5? Okay. They're both sensible choices. Neither one of them will be better or worse. So, and redraw. So we get a simpler angle negative 4 pi over 5. All right, fair enough? People feel good right now? The next step is to replace that angle, is to see if that angle is in the right quadrant to be in the range of inverse sine. Is step 2. Is this in? What quadrants give the range of inverse sine? Quadrant 1 and quadrant 4. And maybe there's quadrant 1 and quadrant 4. Is it in either of those quadrants? Nope. So we need to do a reflection that resolves the y value. So what axis do I need to reflect over? Reflect over the y-axis. So we need to reflect over the y-axis. And maybe I'll pull up the relevant page in the notes. If you reflect over the y-axis in terms of symmetries of the unit circle, that corresponds to replacing the angle theta by pi minus theta. So let's replace that angle theta by pi minus theta. So that means I will replace negative 4 pi over 5 by pi minus theta. Pi minus 4 pi over 5. All right. And I can tell my brain's not working so hard right now. So I'm not going to try to do that addition because they're lots of people in the room right now. What's pi plus 4 pi over 5?
9 pi over 5.
9 pi over 5? Cool. People agree? All right. So there's a simpler angle. So there's a new, simpler version of this angle, in that it's at least in the right quadrant. Okay, cool. So that is now at least in the right quadrant to be an output corresponding to inverse sine. So are we done? We still need it to be in between negative pi over 2 and pi over 2. Is it in between negative pi over 2 and pi over 2? No. 9 pi over 5 is almost 2 pi. It's too big. But it's in the right place on the unit solver. So that means I've just like over-rotated. So to get to 9 pi over 5, you start here, and you rotate all the way around the circle until you get there. Oh, so that means that like it's too big. So if I subtract 2 pi from that, I'll get to the same point on the unit solver. But hopefully now it won't be too big. That makes sense? So let's take the same angle and subtract 2 pi from it. If you like, that'll be the same as figuring out how far down I need to rotate to get there. So let's do that. Not in between negative pi over 2 and pi over 2. So that means we should subtract 2 pi. And we're subtracting 2 pi because it's too big right now. I need to make it smaller. So 9 pi over 5 minus 2 pi. I mean, I don't know, the only thing that's difficult now is like, how do you work with fractions? And so if you feel comfortable there, then like you're already done.
Negative pi over 5.
I hear a negative pi over 5? Do I hear a second for negative pi over 5? All right. I think I agree. Anyone want the reminder about how to combine fractions? Okay, that's good. That's good. I'm going to do it anyway. It would be like 9 pi over 5 minus, I need to get a 5 in the denominator, so I need to multiply the top by 5, so that's 10 pi. Oh yeah, that's negative pi over 5. And now final sanity check, is that in between negative pi over 2 and pi over 2? Awesome, so well done. And let's close by making that same sanity check. I have enough time to make it, so I should. Let's pull this back up. I wanted to plug in 25 pi plus pi over 5. So let's do that. X equals 25 times pi plus pi over 5. And Desmos didn't do anything silly with parentheses. 25 pi plus pi over 5 is like pretty big, so. About 2.53, oh no, that's cosine. About negative 0.628, is that pretty close to being pi over 3? Pi over 5? Yeah, right, pi is about 3. I'm gonna use that to get my ballpark. You have a calculator, so you can use that if you want. That's about negative pi over 5, yeah, that's about negative 0.6. Groovy. So, homework is due today. Maybe I'll say that in particular the homework that I just assigned today is one that has quite a few moving parts because you're doing this computation. So maybe start that not the last minute. Even if the other person who successfully does that on many of the other walks, don't do that on this whole walk. You too. You too. I meant to ask you, how was the previous?
Cool.
Did you actually get to a place where like
I looked it up, and I was literally, like, total center, and then I was standing next to the light bulb, the satellite picture showed the total. And it was really, really cool. I could see little pink, because we met some random strangers who lived there, and they went to hang out with them, they lived there, and telescope and stuff, and I got to see little pink, or, it's some weird name. Little red things that appear when it's doing like a diamond. So it was, you know, I'm like, because, you know, the diamond crazy thing appeared. So it was, you know, really, really cool. And I was gonna ask you, class after this one, are you full in that class too, or next week there's a couple things I want to sit my repeat, two class, you know?
Oh, yeah, there's space. Yeah, if you want like,
Double review on some of it,
if you want to catch the matinee and the sequel, you can do that.
Yep, okay.
I'm just gonna ask real quick, I have a Thursday tournament that I have to drive to tonight, is there any chance I could turn something over to tomorrow if I can't get it done tonight? If not, that's fine.
Oh, yeah, so two things, send me this in an email. Is the Frisbee group like you possibly related?
Yes, it's a club.
It's a club, okay. So you have like some sort of reasonably official university looking thing that says that you're going to this thing?
I mean, I can ask for one, yeah.
Yeah, I mean, just to get you into the habit of doing that, I'm gonna say like, try to get one and send it to me.
Okay, cool. I will ask about that.
Cause like, yeah, I'm fine with it, yeah, I'll be.
Okay, sounds good.
When you do submit it, like, there's a little comment box, like type into that comment box, like, I want you to listen to me.
Okay, sounds
So
good.
that's how it would be okay.
Thank you.
Thank you. See you.
After much pain with that wonderful review, I only got one wrong. I stared at it for many hours, and I went to the math lab today, and they helped me with it in like 4 minutes.
Oh, good.
It hurt my ego a little bit, but, oh,
Well, none of the problems are like intended to be super hard. Which one was it?
it's the triangle one.
Okay, yeah.
And I am horrible with geometry to start off with, which is the base of this one. So it wasn't too hard once it was all put in front of me.
Yeah, so somehow like, if you remember, like, it's a right triangle, so you should think about SOHCAHTOA.
Yep, and that's where I wasn't like, I didn't realize that I could just pop a 90 in for that. I wasn't thinking about the right triangle, I just didn't know. That was important.
Mm-hmm.
Anyways, I'm
So-
just happy it's taken care of now. It was driving me crazy.
So if you had like done that before the exam instead of after, you probably would have gotten like the bonus problem on the exam day.
Maybe,
Alright.
maybe.
So I guess that means that on the like points back review, you went from like a 90-something percent to 100% on that?
I haven't entered that in. I have like a 90 something. That's the only one that was off. So when I enter that in, it will be.
May I say something that you will find very frustrating? Because of the way that I use the review for points back, there is no difference between getting a 92% and a 100% on that one. In terms of like your final grade.
I think I'm still gonna enter it in.
Yeah, you should.
Oh, I didn't know that, but okay.
So it's the way that here's the way that I use the review for points back. If you already have a 90% or above, I don't look at the review for points back. If you scored below a 90% but you did worse on the review for points back than you did on the actual exam, I don't take points away. If you did better on the review for points back, then I will replace your exam score with either the score you got on the review for points back, or your exam score plus 10%, whichever is less. So I just replace your exam score by the review score to a maximum of 10% of points back.
Okay.
So if you already had over 90%, I would just like cap it up off of 90% anyway.
I'm not worried about that.
Okay.
There's no time.
But like regardless of all of that, like the nuts and bolts of how I compute the exam grade doesn't matter. You can just do your best on those things. The strategy is the same on your end, I don't think.
Yes, Brian, I'm comfortable with the testing side.
Okay. And then any point during your college career you find is like really spiking or getting mad, that like that is a diagnosis.
After this, I'm done.
Oh, okay, so
Yeah.
it's not so relevant for you.
No, I'm not going for a master's here. I was hopeful when I was younger, but I'm like, I'm done. I'm so done after. I was going to regret at least for a long time.
Depending on what you want to do after our university, what is your plan for after graduation?
So, I'm a criminal justice major, and right now, I landed a full-time job at the Bolton House, so I'm thinking of getting there. And once I graduate, it's looking like they'll shift me over to legal advocacy. So like right now, I'm doing screening orders, divorces, that kind of thing, and I'll just be doing that during the day, like doing court watch and stuff. So we have people sit in on relevant court dates and provide support, working with the witness.
So,
Yes.
yesterday you were talking about, you were debating on whether or not you were gonna give an extension on some of those.
Oh yeah, so there was the issue with like one of the problems had a typo, right?
Mm-hmm.
I have
Well-
pushed that deadline back to Monday.
Okay.
Was there another extension?
What about the other ones?
Oh, no, we'll type on those ones, as far as I know.
No, there wasn't. Anything.
Yeah, I mean, so here's my feeling on these in general. Do you feel like if I gave you some more time, you would like spend the weekend on those problems? Okay, cool. Like try to get them done tonight. If you're feeling like extremely panicky, like you're not going to get them done tonight, then shoot me an email saying like, here are the ones that I just didn't get to tonight. Is it just like a time management thing, or is there something you want to talk about?
Yeah, it's mostly a scheduling thing, where it's just like
Okay.
I've been pretty loaded on tests and prepping for those this week, so
Okay.
I just haven't really had a chance to get to them until like this morning, so
Yeah,
it's like,
I'd say get them in ideally Saturday, well, ideally tonight.
yeah, I can get a couple of
Then
them
ideally Saturday at the latest Sunday.
Yeah.
And like, shoot me an email on like tonight if you decide to take me on this.
Mhm.
And then when you submit it, like, put a little comment, there's like a comment field.
Oh,
Where
yeah,
you
yeah.
can say like, I said I would take this one.
Alright, sounds good.
Cool. And that applies to everyone, right? Like, as long as you're not like taunting everything in late. I'm fine with like, something's going on tonight, as long as you communicate.
For the web work, does it take points off? It's like late?
No.
No?
Um, yeah, so there is a deadline on each of the web walks,
Yeah,
but they
but like if we got them done on like Sunday instead of today, would it be fine? Like I have all the open-ended questions done, just not.
Yeah, so here's my thought on the web walk deadlines. The deadlines are there as a guideline for you. Like, try and keep up with the web walks, and like, have them more or less completed until you're happy with by the deadline. But then maybe like, you don't have 100% on all the web walks, but you don't even find time to go back to them. Going through, like the web walk problems you haven't completed in advance of the final exam is a great way to study. So if you don't have 100%, the deadline to have all the points you want on the WebWalk is after the final exam. At some point after that, I'm going to hit like an export button in Canvas, and then like the copy of the grade spreadsheet I'll use won't be connected to Canvas, so it won't make any updates anymore. So there's the actual deadline, but like the deadline in the syllabus is the end of the day on the last day of class for all finals. And otherwise, like there's no points on the day. WebWalk. Yeah.
Follow-up. Is there, it doesn't take like a week normally to do exams, 2 weeks, how long for grading, or do you think that's?
I mean, I've been really good about it being less than a week between, and I should be able to manage this.
Okay.
I get annoyed with myself if it takes more than a week. And before that point, I would also be annoyed if you were getting impatient. Because like,
So that's a lot.
So the other thing that you might be noticing about me right now is I'm a little bit rambly and disjointed. I have to apologize for this on my end. My dog had me up between like 1:30 and 3 this morning, and then I have an alarm that goes off at 5:30. So my sleep was kind of cut down last night. That being said, let's get started. And the first thing that I want to mention is